All right, everyone, welcome back to the mythical third session of the day. Now we'll have Marco Girardi talking about a general syntax for non-recursive higher inductive types. And just a reminder to hold your non-essential questions until the end of the talk. We'll have a 20-minute talk and then 5 minutes for questions. All right, so Marco, take it away.
Okay, thank you very much and good evening to everybody. I'm Marco, a PhD student at the University of Trento, and I will talk about the work we are currently doing on the syntax for higher inductive type, in particular focusing on non-recursive higher inductive types in this talk. Higher inductive types in homotopy type theory are without doubt a very important feature. Indeed, there are many interesting examples of higher inductive types which are everywhere throughout the literature. We have geometric higher inductive types, so to say, like the circle as one, the interval, suspensions, and what else. We have higher inductive types that mimic categoric constructions, like the push-outs, for example. And we have other more particular higher inductive types, like propositional truncation, which is an example of recursive higher inductive type. It is rather easy to give the introduction rules for these types, as we are accustomed to for ordinary inductive types. We just give a list of constructors that in some way describe how the type should behave. But the elimination is quite a bit trickier. In this regard, the homotopy type theory book is rather vague, in the sense that it basically gives you some examples, it tells you how to do that in the case you have a higher inductive types with non-recursive point and path constructors, like S1, for example, but it doesn't tell much more. For example, it gives the example of a higher inductive type with level 2 constructors, which is the torus, but it does not tell what its induction principle should be. And even for recursive higher inductive types, it is rather vague. The problem here is that we lack a satisfactory syntactic formulation for higher inductive types. And I mean this in the sense that we do not have a general schema that tells us what we are allowed to do with constructors. And most importantly, once a list of constructors is given, how we can extract the inductor for the higher inductive types we are defining. There are some attempts, especially in the recent literature, toward these goals. In particular, the work by Kaposi and Kovacs, which is much more general than what we are doing. It is with higher inductive types, but it relies on an external type theory and is, in this sense, kind of complex. We would like to have a more direct approach to this problem. The idea here is that we do not want to go out of the syntax of homotopy type theory so that we can reuse what we know about the proof theory of homotopy type theory. Here in the talk by homotopy type theory, I usually mean the type theory presented in the hot book. So we have cumulative hierarchy on universes and everything is in the book, basically. Our goal is basically to extend the results known about this theory. In particular, in the PhD thesis of Roberta Bonaccina is proven a normalization theorem for HoTT with ordinary inductive types. And we would like to extend this for higher inductive types as well. In this regard, we propose a syntax for non-recursive higher inductive type, which mimics the style of what's done in Bonaccina's work. And the main idea is to mimic what we do for level 1 constructor to higher constructors as well. In particular, the key point here is that to eliminate one constructors, we need the concept of a path that lies over this constructor, a proof along this path. And to generalize this, we need to generalize the transport function to higher paths. Once this is done, we can generalize the concept of path line over to higher paths, and then we can exactly mimic the constructor, what we do for level 1 constructors to higher constructors. We will see that this will introduce some problems at higher levels with the computational rules, and we'll see how to solve this as well. consider now this example that we'll keep in mind throughout the talk to get an idea of what we are doing. Here we have 3-point constructors, N, S, and P, 3 paths, W here on the west, and 2 paths on the east here, and a level 2 constructor that is basically a surface connecting W to E1 concatenated E2. If we want to perform induction on this type using a type family C, we would need basically an induction method for the level 0 constructor, which we know as usual where we have to look for those. We need an induction method for the level 1 constructor, which of course, as stated in the hot book, has to be something of this type, which is basically a path connecting the proof of N and the proof of S that lies along W. This is a path line over W and is defined in the hot book. And for the level 2 constructor, we want to do exactly the same thing. We would like to find the induction method for the constructor field in a type that resembles something like this. The proof of a path connecting the proof of W and the concatenations of the proofs of E1 and E2 that lies over the path field, where this is, in analogy of what happens with the level 1, an abbreviation for this identity type here. So we have a transport 2, which is yet to be defined, of course, along field of CW equals to what we have here on the right-hand side. From this, we can see that the natural argument we have to pass to the transport 2 function is actually a pathover at the previous level. Here, CW is a 1 pathover. And in some sense, what does this transport 2 function we would like to define? It changes the underlying path. Here, CW was a path line over W, and its output has to be something that is a path with the same endpoints, but that lies over the concatenation of E1 and E2, which was the other endpoint of constructor field. How can we give this definition? Basically, we do this definition by we define transport N along an N path chi of C alpha, which is an N-1 path over line over alpha, as the usual transport function in the family of N-1 path over along the path chi. This just changes the underlying path. Once this is done, we can easily give a definition of N path over as the usual abbreviation as it happens for the level 1 case. Okay, now we want to give an idea of the rules of the calculus we are proposing. Most of the rules, almost all actually, will be introductions of constants in the calculus, and this is done following, again, the work of Bonaccina, because it makes the proofs about the proof theory a lot easier. In our example, formation rule is not exactly very interesting, because we just say that T is a type, but in general, we may want to allow a type to have formation parameters. For example, suspension, the suspension type is a constant sigma that takes an input a type and performs the suspension of that type. Or the push out needs quite a long list of parameters to be formed. So this is in general the formation rule. So we have introduced a constant T of the type, which takes an input the formation parameters and outputs a type that lies in some universe. As for the introduction rules, in practice, what we do is we just give a list of constructors where each constructor can refer to previous ones. For example, if we consider the suspension over a type A, we have 3 constructors, N and S, which are point constructors, and then the constructor for the meridian that takes an input as an input a point of the type A and outputs a path between N and S. Here we are constructing a path, so this is a level 1 constructor. Again, the idea is that we have a rule introducing a constant for each constructor. And in general, how do we do this? Let us denote by Ki the ith constructor for the higher inductive type. And what is Ki? Ki has to be a constant which takes an input the formation parameters if needed, some input arguments if it needs it, of course, and outputs something Hi here. What is Hi? By Hi, I denote a path space which is at level n in T. Okay, again, what is a path space at level n? a path space at level n is a concatenation, a path between concatenation of previous level n-1 constructor. Basically, each one of these p is a previous constructor kh instantiated to some sequence of terms th, possibly inverted, of course, and basically it's just what you would expect. At level 0, there is only one type space, which is T itself. In that case, we are constructing points of the type we are defining, and so it's just the type itself. Okay, now we want to go to the elimination rule. And again, what we have to do is for each constructor, we have to provide an induction method. We have already seen that for level 0 and level 1 constructor, it's rather easy. We know from the hot book where we have to look for these induction methods. Here, we say we have to look for the induction method for n in this type here. And we say that Cn is the lifted path space of n of type T. This, in analogy with what happens at level 1, here we have W, which is of type n equals s. We have to look for the induction method in the space of pathover where the endpoints are the proof of n and the proof of s, and is a one pathover lying over W. We say that this is the lifted path space of W of type n equals s. And similarly for level 2, here we have to find the induction method for fill, and we find it in this path space, in this pathover space here, for the space of two pathovers over fill, where the endpoints are the proof of W and the concatenation of C1 and CE2. And we say that this type here is the lifted path space of this constructor here. Okay. Note that here the asterisk denotes just the concatenation of two pathovers, which is rather easy to define by path induction on the underlying paths. Okay. We've talked about lifted path space in that example. In general, what is a lifted path space of a constructor? Well, if Ki is a constructor of our higher inductive type, we consider Ki instantiated to a proper sequence of variables, which is a term in the type space Hi. The lifted path space of Ki fx in Hi is this type here, where basically you take the path space you had before, replace path concatenation with pathover concatenation, path inversion with pathover inversion, is not an ordinary path, but is a n pathover that lies over our constructor we are lifting here. And all of these cursive P's are, well, the P can only be a previous n-1 constructor instantiated to a sequence of terms. The cursive P is basically you replace the constructor with its induction method. That's exactly what you would expect when you perform induction. Intuitively, what do you do? You want to replace all the constructor with the proofs of that constructor in some sense. Note that here we are allowed to use CH because KH is a previous constructor, and so CH has already been found in some sense. That's exactly what happens here in the example. For example, when we are looking for the induction method for W, we are looking here in this pathover space that relies on Cn and Cs, which are the induction method of the previous constructors N and S. Okay, so the induction method for the general constructor Ki is simply to be found in this type here. We have the same sequence of pi, and finally the H is just replaced with the cursive H. Again, the elimination rule is stated as a constant introduction rule when we introduce an inductor which has the proper type, which is basically a long sequence of pi's with all the induction methods, and finally yields the desired dependent function out of the type T we are defining. Now, if we want to talk about the computation rules, we first have to define what the dependent application of a dependent function to a higher path is. This is easy to do by path induction on the n path chi here, and basically the output of APD ng to chi is a path over at level n that lies over chi, where the endpoints are the previous level APD of the endpoints of chi. At level 0, we define APD 0g to be exactly g. In fact, APD 1g becomes exactly the APD we have in the hotbook. Now, let G be the dependent function we get by performing induction on our example, and let us try to write the computational rules and see what happens. At level 0, we have no problem. G of n is the induction method of n, and these are propositional, judgmental equalities. At level 0, exactly, we are following the hotbook in this choice. At level 1, we want just propositional equalities. So if we want to say that APD1W is equal to the induction method of W, and this is just propositional, so we introduce a constant here of this type here. If we want to do the same thing at level 2, we have a problem, because we would like to write this, but APD2fill has this type here, while CFill has this type below here. And the two are not definitionally the same, so we cannot form this identity type here. However, unsurprisingly, the two types are actually equivalent. In fact, APD2fill had this type here, this pathover has this type here, is in this pathover space, and the left-hand side is actually equal to CW thanks to the computation rule. While on the right-hand side, it's just a little more work. We have to first distribute APD at level 1, and then apply the computation rules to APD1E and APD1E2. If we take APD2fill and concatenate this path on the left and this path on the right, we get a pathover between CW and CE1 concatenated with CE2, which is exactly the type of CFill. So the types now are okay. In fact, this means that we can construct an equivalence that takes between this pathover space and this other pathover space, defined simply by the concatenation of the paths here. And finally, we can state our computation rule in this way. We introduce a constant CFill that is a propositional equality between this equivalence applied to APD2fill and CFill. Now it's type checks. Note that this actually does not strictly depend on fill. We can define an equivalence in this way no matter what the particular path we have here. And in other words, we can abstract fill out of this equivalence. So we get an object of this type here. And this will become useful in generalizing this fact. Because of course, when we go to even higher constructor, we have to keep in mind that at previous levels, we had to fix things with these equivalents, and this might get cumbersome. However, we have this lemma, which admittedly is not quite readable, not easy to read, but this basically states that if we have an equivalence between pathover spaces that do not depend on the underlying path, here gamma is in the pi, and if you have a path between two paths that are here in x equal y, then if you have this pathover space from C alpha and C beta, where these are pathovers on alpha and beta, this is actually equivalent to this pathover space where we basically apply the equivalence on alpha and beta on its endpoints. And why is this useful? Let us get back to our example to get an idea. Of course, at level 1, we did not have to fix anything, but pretend we had to at the moment. So pretend that we had to state the computational rules for W, E1, and E2 like this. So we have an equivalence applied to APD1W equals CW. Okay, of course, as we stated, this equivalence does not strictly depend on W, so we actually have a fiber-wise equivalence of this type here. So when we take our APD2fill, which lies in this pathover space, we can apply our lemma to get the phi here instantiated on W on the left-hand side and on E1 concatenated E2 on the right-hand side. And then we can do what we did before. In particular, here on the left-hand side, we can use the computational rule for CW to get, again, the induction method for W. And on the right-hand side, we need a little bit more work. We have to distribute the APD again, as we did in the previous case, in the previous example. And then we have to distribute this equivalence, which can be shown to be possible when it's properly defined. And finally, we can apply the computation rules to get in our desired right-hand side. So in this way, we can
Is it me or is it?
No,
It's not you.
He's frozen for me as well.
It's not you. It's yeah. Okay. Oh wait, the speaker is back.
Okay, he's back. Okay, we lost you for a moment there.
Okay. Yes, of course, connection had to be unstable exactly in this moment, but okay. So how much time did you lose?
About a minute.
About a minute. So
Yep.
okay. So did you see this slide?
Yes, I think you cut off while toward the end of this slide, maybe.
Toward the end of this slide. Okay, well, basically, this slide, should I redo this slide? Well, it's not much time. Okay, so here, if you pretend we had to do the fix at level 1, we just use the lemma to get the phi's in place and then distribute the APD, then distribute the phi, and finally we can perform the computation step using the computation rules we had at level 1. The idea is exactly this and extends generally at higher levels without too much trouble. It's just cumbersome to write. Okay, about future work, of course, this syntax proposal at the moment just handles non-recursive higher inductive types, but there are some interesting recursive types, for example, truncations or localizations, and we would like to be able to handle at least a subset of recursive higher inductive types. And we are currently working on this aspect. In fact, we have a small generalization that allows for truncations as well. Then, once we have generalized it enough that we are satisfied with the work, we will try to extend the proof theoretic results in Bonaccina's PhD thesis to our setting, in particular focusing on normalization theorem. And another aspect that we would like to focus more on in the future is to have a better comparison with other works, so that we can better understand what the advantages or drawback of our approach could be compared to other works in this area. And this concludes the talk. Thank you very much.
Okay, thank you. And let's all clap silently. All right, and I think we have just a few minutes for questions. So if anyone has a question, can, I guess, go ahead and unmute yourself. Let's see if anyone has...
Yes, I have a question. So for the iterated path space on the side, you allow composition of paths and inverses, right? Do you...
Basically in the constructor, right?
Right, in the constructors.
Okay, yes, in the constructor I allow concatenation and inverses of paths.
Right. Did you look at allowing more things? For instance, if you have two-dimensional paths, you could have both vertical and horizontal composition or other things like that. There are a lot more operations you could have.
Oh no.
Did you look at that?
I can't get it.
Okay, admittedly, I have never thought about having something like horizontal composition of two paths allowed in the constructor. It might be worth looking into it in the future. I don't know. I should try it and see if it becomes something manageable with a bit of intuition. Basically, allowing just for concatenation of paths makes things rather easy when you have to find the eliminator and the type in which you have to look for the induction method.
Right.
Reasonably, I think it should be possible to do it for horizontal concatenation of paths as well, but I'm not sure. I'm just thinking of it right now out of the top of my head.
Right, but then there could be many other things like the associativity equivalence is also something, some coherence law that you could put on the side of some equation, and then you would need some dependent associativity or something, and so on. So that might be also future work to see how you can extend that.
Yes, yeah, of course, we could, another possible direction in which we could extend this work is to see what we could allow a constructor to construct paths between, of course. You should have to think about some examples to get an idea. If you have any suggestion, you can send me an email. I'll gladly look at it.
Right. Thank you.
Okay, thank you.
Okay. I'm not sure if we have time for anything else or not. Maybe if someone has a quick question, because we ran it slightly long. All right. Well, I guess I'll ask. So this is slightly different, but do you know about? There's been some work on doing this for cubical type theories, where a lot of some of these problems go away because the you get the eliminator computing strictly on the higher constructors as well. So there's less this sort of coherence that you have to worry about. I was just wondering if you were aware of that, or if you had any comments on you know, if how you think it might relate to what you're doing.
I have to admit I do not know that much about cubical type theories. I know they exist and they basically solve a lot of problems by making things compute rather easily. I know there are some related works which basically, maybe, who was it? I don't know. There was a work maybe by Moneclay, I don't remember right now the precise reference, that proposed a groupoid model where for hot with higher inductive types which allowed constructors up to level 2. And since in that model you could actually have judgmental equalities for higher level for the level 2 constructors, they decided to use judgmental equality for those constructors as well. And of course, all the computation rules become a lot easier because there is nothing to fix. Basically, everything becomes of the right type automatically.
Right. Okay, well, I guess we should probably leave it there. So let's all thank the speaker silently again.
Thank you again.
Okay.